Okay, but the question here explains exactly what's happening. I'll talk through that as I need to. After these two A and B collide, then A's got 4 in its original direction, and you've got to calculate the speed of B. So I'm going to do the first part, do in blue. I always put them like this. Mass of this one is 0.8, and the mass of the other one is 0.2. And I put the velocities before, that's 6, and that's 2 as shown. And this one here is 4. And this one here, I don't know, it's going to have to go to the right because it cannot go to the left, or else I'd have to pass through this one here. So I can call that V, and that's A, and that's B. And I've got lots of these here, it's going to be worthwhile keeping that done. And I know that total initial momentum equals total final momentum. And I also know that direction matters. And so I've got 6 times 0.8, so mass times velocity, well, velocity times mass in this case, as I've written it, 6 times 0.8. And then this bit is going to be, that's minus 2, so I'm going to have to subtract 2 times by 0.2. And that will be our final one, which is 4 times 0.8 plus 0.2 V. And that will say that 4.4 equals 3.2 plus 0.2 V. And so V will equal 1.2 over 0.2, which equals 6 meters per second. And that's the first part done. Second collision between C and D over here. It says mass that they coalesce, which means they stick together. So that means they'll leave with the same velocity. So again, part 2, do it up here. One object, label them together. C, D, initial it's 5 and 0 meters per second. And finally, I should perhaps use a different letter. I'm going to use V again, but they're both going to have the same velocity. As always, total initial momentum equals total final momentum. And initial momentum, direction matters again. It's 5 times 0.3, and that will equal our final momentum. Oh, I should put the masses in. That's 0.3, that's 0.1. And the final momentum, since they all stick together, that will now be 0.4 times by V. And so V will equal, that's 1.5 divided by 0.4, which is 3.75 meters per second. That should be a 1. Okay, and now part 3 I will do in purple. The third collision is between B and the combined particle, after which no further collisions occur. And that's quite important. In fact, very important. Calculate the greatest possible speed of the combined particle after the third collision. So here I've got B and I've got CD. So B is 0.2 and CD is 0.4. And this one here, it comes in there. B, we've worked out it's going at 6. And this one here is going at 3.75. And we want to work out the greatest possible speed of the combined particles. We want to work out this one here. I'll call it V again. A bit confusing, but there we are. And this bit's, this got to be the greatest possible. So this one's got to be as slow as it can possibly be. Well, this one, A, keeps on travelling at 4. And so if there are no further collisions, this one here will have to be keeping going at least 4. Because if this one were to be going at, say, 3.5, then the A one would catch it up. So it cannot be 3.5, that one would have to be 4. And that's the bit which enables us to do it. And then now it becomes straightforward. So total initial momentum equals total final momentum. And that'd be 6 times 0.2 plus 3.75 times 0.4 equals 4 times 0.2 plus 0.4 V. And that gives me 0.4 V equals 1.9, and so V equals 4.75 meters per second. and quite straightforward. But that was the one bit really important to spot. Hopefully that's clear enough, and that's question 4 done.